first thing you need to know is the average rate of change for a quantity over a period of time is the change divided by the time elapsed. Okay, so go ahead and write this sentence. This is a really important sentence. Average rate of change. You can just call that A rock if you want. A rock. Is the average rate of change. Is the amount of change divided by the amount of time elapsed. Everyone got that sentence? We'll move on. Okay, can I move on to the next page? I'm going to give you a more generic definition that doesn't use time, because, listen, it's really easy for us to think, when we hear rate of change, our mind typically thinks to moving cars. Like, we think about moving cars, and you know, your bank account is changing over time, and what's the rate of change, and what's the rate of change between the 5th and 7th year. That's all average rate of change, but we always think time, you know? We don't have to think time. There's a more general definition of average rate of change, and that's this one. The most general definition would be the average rate of change, or you could say AROC, of a quantity over an interval is the amount of change divided by the length of the interval. It does not have to be a time difference. So it doesn't have to be T sub f minus T sub I, you know. Initial time minus, or final time minus initial time. It doesn't have to be a delta t, it can be a delta anything. Okay. And there's a formula that goes with this one. It's right there on the board. The average rate of change, also known as the slope of the secant line, is f of x2 minus f of x1, all over x2 minus x1. This formula is straight out of the pre-calc book. And you'll see it in a moment. I'll do an example. It looks just like last year's 2.3. It's this year's 2.4. First example. Okay, so the reason I'm putting this sentence up is because, again, I don't want you to think everything changes with respect to time. Right? Let me give you just a real life example of this. Right? Let's say you have a balloon, right? And you buy the balloon, and it looks like this. And that's what balloons look like when you buy them.
Oh, the unballoon.
It's not inflated, right? Okay, so now let's inflate it. So you inflate it, it starts to look like this, right? And then you inflate it some more. Now it looks like this. This is fun. I'm drawing balloons. Let's assume it's a sphere, okay? For all times after t equals 0. So not this guy. But let's assume that it's a sphere. All right? So what's the volume right now? 4/3 pi r cubed. That's the formula. What's the volume now? 4/3 pi r cubed. Right? It's changing with respect to time. But I don't have to talk about its change with respect to time. I could write down its volume as a function of radius. Right? That's typically what we do anyway. We would write volume as a function of radius is 4/3 pi r cubed. And now it's bigger, so we can write 4/3 pi r cubed again. This time we're thinking of a different radius. So what was the average rate of change? Well, it would be this minus this divided by the difference in radii, or the difference in time. Depends on how you want to talk about it. You want to talk about how the volume is changing with respect to time. If you want to talk about how the volume was changing with respect to the radius, there's lots of ways to set up an average rate of change. Okay, so here are some possible AROCs you could write down. You could do average rate of change with respect to time. WRT means with respect to. That would look like this. 4/3 pi r2 cubed minus 4/3 pi r1 cubed all over t2 minus t1. In which case you would need to, you basically have like the volumes on top and the times on the bottom like that. Okay? Or you could have r2 minus r1 on the bottom if you wanted to do this with respect to radius. So average rate of change with respect to radius. I realize now I didn't have to write WRT 2. WRT means with respect to 2. Okay, so you could also find average rate of change, finding the difference in the volumes, but with respect to radius is what I'm saying. So you could do R2 minus R1. It just depends on the question, it depends on what you want to study, but I don't want you to think that everything is measured with respect to time. It's not true. Okay. All right, let's go on to the next example. This is our first real problem. Find the average rate of change for the given function over the given interval. The function I'm going to use is x cubed minus 2x plus 1, and the given interval is from -2 to 4. So we're going to find a rock for the given interval. Notice this question has nothing to do with time. Okay? Okay, so let's see what this graph looks like. Let me turn on my calculator, delete some of this pre-calc stuff I got going. Don't forget to write down that domain, okay? -2 to 4. All right, let's enter the function. So it's x to the third minus 2x plus 1. Okay, and then you can graph it. So right now I have my window set for a pre-calc problem. So my window's not real good. Let's go to window and let's make it go from -2 to 4 like it says. So let's go -2 to 4. And for y min, I'll just do -5 and y max +5. Let's just see if that works. I might need to fix that. -5, +5. Okay, let's graph that thing. Not a bad graph for a first zoom. Sometimes I have to fix those. But we're looking at between -2 and 4. Let's see, where is x4? Okay, that's actually kind of far out to the right. Okay, I'm going to make my y max a lot bigger actually. I'm going to make it 70. Alright, because I have a feeling f of 4 is pretty big. Okay, there we go. So what exactly is this question asking you to do? Well, we're asked to find a rock. And we're supposed to go from -2 to +4. So what you're supposed to do is go from where x is -2 all the way out to where x is 4. Oops, right there. See? And you're going to be finding the change in y divided by the change in x. So it is the change in the function divided by the length of the interval. Okay? So basically you're finding the slope of this line is all you're doing. That's all you're doing. You're finding the slope of that line. Okay, so first you need to kind of know where those 2 points are. You can't do a rise over run calculation if you don't know where the points are. So let's get those points figured out. Okay, so this is the point -2, f of 2. So let's go over here and calculate that. So -2, f of 2 to the point 4, f of 4. So we're going to try and find the average rate of change. Okay, so what is f of -2? You got to plug in the -2 here. So what does that give me? -3. Okay. And let's go to the point 4. So what is 4 cubed minus 2 times 4 plus 1? 57. Okay. So we're going from the point -2, -3. We're drawing a straight line to the point 457, and we're just finding the slope. This is child's play. This is simple stuff. Okay? So we call it average rate of change, but it's really just the slope of that secant line. So we call that m sub sec. Okay? So we're just going to do 57 minus negative 3 over 4 minus negative 2, which gives us 60 over 6, 10. So the slope of that line is exactly 10. But we call it the average rate of change. Okay? Any questions on that? All right. Just to go a step beyond that question, you could also find the equation of that line. So let's do that real quick. So this is the average rate of change. Let's add a question. Okay? Let's add the question, what is the equation of the secant line? Because that line that I drew that connects those points, that doesn't just have a slope. That has its own equation, right? Okay, let's get that equation. That's not hard to do. Do you guys remember this line? This thing, y minus y1 equals m times x minus x1? Pretty handy. This thing's great. Okay? If we're going to find this equation of the secant line, then by m, what we mean is mc, the slope of the secant line. Okay, so here we go. Let's plug in the numbers. We already have everything we need. y1 was negative 3. The slope of the secant line was 10. So my answer to this part of the example would be y plus 3 equals 10 times x plus 2. If you have been a fan for many years of the y equals mx plus b form, I would strongly encourage you to reconsider switching over to the point slope formula line. So if you've always been the y equals mx plus b Nazi, and you insist on doing every problem with y equals mx plus b, I really think it's time to switch to this. Point slope form is much faster in calculus. Okay? If you want point slope form, distribute your 10 and bring the 3 to the right side.
So you don't have to make that the answer? You can leave it like that?
Yeah, you can. This is the y equals mx plus b form if you insist. Okay? This is 10x plus 20 and I move the 3 over. But when you're finding the equations of the line, this is quite easier. A lot of formulas in the book look like it too. Okay, so that we did like a step beyond the question there. Okay, let's go on to this one. You're going to see a problem like this in the homework, and I don't need to do this whole example. I just need to kind of get the ball rolling so you understand it. This is a story problem about some guys on the moon, and one of them drops a wrench off of a platform, and it lands on the roof of their little moon station. Bang. I don't know, actually, can you hear it when it hits the roof on the moon? Some guy drops a wrench from way up high on the moon and it lands on the roof. Can you hear it?
Yeah.
Okay. There's an atmosphere on the moon. I suppose you can hear it. It's just, yeah, but when the wrench hits the
It makes
the
a
roof.
sound.
So are there molecules to carry the rarefactions and expansions of air, or the compressions of air? You know what I'm saying? If there's no air molecules, this is a distraction, but if the wrench hits the roof, right, it's supposed to vibrate the air molecules, and that's how it's going to hit your eardrum. Are there air molecules on the moon? Does the moon have an atmosphere?
No.
Probably a thin one. Anyway. The question on this one is just talking about the wrench falling, and it takes 10 seconds. It falls for 10 seconds, and by the time it hits the roof, it's obviously sped up a lot. Okay? So our goal is to actually find the slope of this line right here. Okay, there's a problem with this line. It's not connected to 2 points. It's only connected to point P. So how are you supposed to find the equation of a line given only 1 point? the slope of Q2P, and the slope of Q3P, and Q4P, and they would find all of them. And they would ask, what number is that slope approaching? Okay? So let's just run through this. This is not really very difficult. The points here are, if you look closely, P is at the point 10, 80. And Q1 is at 5, 20. And Q2 is at, it looks like maybe 7, 38 maybe? I'm supposed to say Q2. Q3 looks like it's maybe at 8.5, 56 maybe. And the last one there, Q4, it looks like it's at 9.5, maybe 72. A little hard to tell. It doesn't matter, it says estimate. Okay? So let's just run through these. So if you want to find the slope of PQ1, you would do rise over run calculation using the 1080 and the 520. So your difference in y's would be 20 minus 80. And difference in the x's is 5 minus 10. So this just comes out to negative 60 over negative 5. So that's 12. And then if you want to do PQ2, now you're going to be using the 38 minus 80 divided by 7 minus 10. And that comes out to negative 42 over 3, negative 3, and that's 14 exactly, see? And then you do the same thing with PQ3 and PQ4. And both of these come out very close to 16. Okay, so what's going on here? So I didn't show all the work, but trust me, they come out to close to 16. What's happening? Okay, so the first thing we did is we found the slope of this line here. Okay? That one. And then we found the slope of Q2P, which is that one. See? You kind of have to watch the screen here. Then we found the slope of Q3P, which is that one. And then we found the slope of Q4P, which is that one. Notice that the slopes of these lines I've calculated are all getting closer and closer to the slope of this black line, which is the slope of the tangent line. You see that? So if I had to estimate what number that black line had a slope of, I would probably go with 16. Look how it's getting closer and closer to 16. Okay, so it's just an estimate, it's not a proof, but I think the slope of this line is 16. Now it's saying speed. Why are they saying speed? Okay, let's go back and talk about units here.
Distance versus time.
Right. When you were doing rise over run, right, you were doing 20 meters minus 80 meters, so the top was meters. And then you did, 5 seconds minus 10 seconds. That's basically time. So this whole thing was done in terms of meters and seconds for the numerator and denominator respectively. So one way you can easily figure out what slopes will mean when you're looking at a graph, let's say you're given a graph and you're asked to find slope, you're probably going to need appropriate units, like it says. How do you find them? Just look right here and ask, if I'm doing rise over run, what are my units? Rise would be in meters, run would be in seconds, meters per second. So let's go back in here and let's put meters per second for everything. So this means that between the 5th second and the 10th second, the average speed was 12 meters per second. That's for the first and last point. Okay? When we did the second and last point, the average speed was 14 meters per second on that interval. When we did between the third point and the last point, the average speed was 16, roughly. It's actually a little less than 16. And the same thing with this one. So in the end, these are all meters per second, because they are slopes of a graph where it's measured in meters versus time. And These are the average speeds for various intervals, and this is what we call the instantaneous speed. Let's write that down. This would be called the instantaneous speed at t equals 10. The other ones are all average speeds. So it almost feels like you're doing a limit, right? It almost feels like you're doing a limit. Okay, so let's go on to the next page here. Okay, so Newton is sort of responsible for, that's the picture of him, by the way. Newton was kind of given the credit for discovering the following facts on this page, okay? Let me move some of this junk around. Okay, so you and I might have the question, what does it mean to find the slope? I gotta move this point over to here, and this point onto here. Okay, what does it mean to find the slope of a curve? What does that mean, the slope of a curve? So many of you have studied the derivative already, so you know where I'm going with all this. Okay, but you have to bear with me, because there's some neat historical background to all this. So, what do we mean by the slope of a curve? A curve is, by definition, made of many slopes, right? I mean, if it's curved, it's not a single slope, right? Pick 2 points on a curve, and I'll tell you the slope, right? So what do you mean by the slope of a curve? So let's say that this is the curve, and it's a green curve, and you want to find the slope of the curve. Well, it kind of depends on which 2 points you pick, doesn't it? I would say if you pick 2 different points, other than these, you'll get a different slope. Okay, so this is a weird thing. But what if I said I just want you to find the slope of the curve at 5? Well, that's kind of a problem, because how do you find the slope at 5? How do you use 1 point to find slope? Okay, so what you would do is you would basically think of this as, hey, I'm actually going to switch this around. I'm going to call this 5, and I'm going to call this 5 plus h. Okay? So what I've got going is a point and another point. I'm not really interested in this second point. I'm interested in the first one. I want to find the slope there, but I'm going to go ahead and tolerate this. I'm going to allow this to be the point 5, this to be the point 5 plus h. And now I'm going to go ahead and find the slope between these 2 points. Okay? So let's see. What's the slope of the secant line? The slope of the secant line, also known as the average rate of change, is going to be f of 5 plus h minus f of 5 all over 5 plus h minus 5. Why? Because this is the point 5 comma f of 5, this first point, and this up here is the point 5 plus h comma f of 5 plus h. So all I did was write down rise over run. See it? I just did f of 5 plus h minus f of 5 all over 5 plus h minus 5. The denominator simplifies a little bit, doesn't it? What does it give you? Just h. Right. Okay, so this would give us the average rate of change between the 2 red dots. Is that what we mean by the slope of a curve? No, not really. Because this is a secant line, see? That's why I titled it MC. We want the tangent line. So if you were to ask David, what do you mean by the slope of a curve? He would say, what I mean by the slope of a curve is the slope of the tangent line to a given point on the curve. So let's fill that in here. So then you might ask me, well, how am I going to do that? I've only got 1 point. He'll say, well, why don't you just take the limit now as h goes to 0? Let's just make h shrink to 0. Effectively, what that would do is bring this point and collapse it onto this point. Right? If h were exactly 0, then these 2 points would be in the exact same spot. That is the goal, but we can't plug in 0, can we? Not yet. So you might say to me, well, I can't plug in 0. He's like, well, not yet. But you will be able to after some factoring, because this is going to vanish when you factor the top properly. Okay, well, we don't have a function here right now. so we can't factor the top because it's just a generic f of x sort of thing.
Not yet.
But most problems you can factor or use a conjugate. Yeah, not yet. We'll be able to factor when we have a specific example in mind. Or we can use some other trick. All right, so what is the slope of the tangent line? This is very important. This is called instantaneous rate of change, also called IROC. That's fun to say. Everyone say IROC. Braggarts. All right. Instantaneous rate of change. Instantaneous rate of change. And that would be if you did the limit as h goes to 0 of f of 5 plus h minus f of 5 all over h. So when you limit AROC, you get IROC. I'll write that. The instantaneous rate of change is the limit as h goes to 0, also known as limo, of AROC. So IROC is limo AROC. IROC is limo AROC. You learned average rate of change in pre-calc. Now we're taking the limit, and this will make instantaneous rate of change, also known as the slope of a tangent line. This isn't probably a big deal to you, but this was completely massive to Newton. Okay, when he figured this out, I mean, it was groundbreaking stuff. Okay, this right here is the foundation of calculus. The limit actually had to come first. The limit had to be thought of and invented first. But this is the first application of the limit that really gave us wings to fly in physics and math.
Was he like the only one that like came up with this?
No, Leibniz, I believe, was another guy who came up with it at the same time. Yeah. So it's hard to appreciate this, but he was a physicist, right? He needed to find instantaneous speeds. He couldn't talk about average speeds his whole career. And he knew there was a way to do it, and he did it by using the limit. Okay? Pretty neat stuff. So there are centuries of history that go between this black formula and this red formula. Centuries and centuries of math history. Okay? I'm not a math history guy, so I don't know, maybe it was decades and decades, maybe millennia and millennia. I don't know. It's a long gap. Okay? Because it took someone really smart to get to this one in green and red. Let's go on to the next page real quick. We're getting a little low on time, but these are two formulas you're going to need all year long. Okay? I cannot stress to you enough how important these guys are. Write them down. And as you know, my clock's a little fast, so I actually have about 5 more minutes to kind of show you what problem we will try to solve. And what I'll probably end up doing is just make it a warm-up on Tuesday. So you'll just try this example as a warm-up. Okay, actually, I think I'm going to stop here. I'm going to stop here. You've got two brand new formulas. We're going to apply these two formulas to a specific problem, but we'll just do it on Monday. So make sure you have these formulas written down, and also the one on the previous page, right here, the one in red, very important. So I'll write it on here as well, so you have all three on one page. The slope at A is limo f of A plus h minus f of A all over h, also known as the definition of a derivative at A.